A single strike could silence a planet. Imagine Mars, a world we have long regarded with quiet fascination, the ochre deserts, the faint whispers of ancient rivers, the restless storms that already sweep its thin skies. Now picture that fragile world meeting an interstellar wanderer, 3I Atlas, racing through the void with unimaginable velocity. In such a collision, the calm Martian horizon would vanish in an instant. The impact would tear open the crust, vaporize stone, and ignite a shockwave that circles the planet in hours. Vast curtains of dust would rise, higher than Olympus Mons, spreading like a choking ocean until no sunlight could touch the ground. Mars would not merely host a storm, it would become the storm itself, a resonant bell of dust and shadow that could ring for centuries. Beneath the surface, buried glaciers and frozen reservoirs might rupture, exhaling clouds of water vapor and carbon dioxide into an already poisoned sky. What we would see from orbit is no longer a red planet, but a smothered world cloaked in black, its heartbeat drowned beneath chaos. And yet, within this cataclysm lies the deeper puzzle. How would the fragile magnetosphere respond to waves of plasma and ionized gas? Would electromagnetic storms ripple outward, threatening our orbiters? Would rovers still crawling in silence survive long enough to bear witness, or would they be swallowed whole by the dark? This is not just destruction for its own sake. It is a thought experiment, a lens through which science tests the boundaries of imagination. What would it mean for Mars to endure such a blow? And what would it teach us about planetary fragility, survival, and memory? Tonight, we embark on a new journey where the theme of 3I Atlas versus Mars, modeling the absolute worst case, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. To begin, we step first into the storms. Mars already knows dust as an intimate companion. Its tempests can swell to planetary scale, turning day into twilight for weeks on end. But in the shadow of a colossal impact, these storms could merge into something far greater, a global convulsion of atmosphere and dust that refuses to settle. As grains rise, settle, and rise again, they could veil the planet for centuries, driving a cascade of chemical and climatic changes. Beneath this shroud, the frozen reservoirs of ice and carbon dioxide might awaken, their sudden release thickening the air in violent bursts. And with every upheaval, electrical storms could ripple through the ionosphere, generating surges of plasma that reach into orbit, where our satellites circle helplessly. It is here, in the interplay of dust, ice, and charged skies, that the first true consequences of such an impact would unfold, marking the beginning of a planetary transformation unlike any we have ever witnessed. As the pale ochre disk of Mars grows imperceptibly larger in the void, a moment of profound cosmic significance approaches. On October 3rd, 2025, the interstellar visitor known as 3I Atlas will make its closest pass to the red planet, a fleeting encounter measured in millions of kilometers, yet immeasurable in its scientific potential. This celestial event, however, is poised to unfold against a backdrop of terrestrial silence, as the United States government enters a period of shutdown, furloughing the vast majority of NASA's workforce and casting a shadow of operational uncertainty over its orbital assets. A historical window opens on the very day a nation temporarily turns out its lights who, then, shall stand as the sentinel for this voyager from the depths between the stars. The immediate, pragmatic explanation lies in the meticulously drafted contingency plans of the world's space agencies. According to the framework of NASA's continuity of appropriations, while 83% of personnel are furloughed, certain accepted activities persist, those deemed critical for the protection of life and property, which includes the basic operation of satellites and the International Space Station. One could logically surmise that the Deep Space Network would maintain a heartbeat rhythm, and mission control centers would operate with a skeletal crew, ensuring that multi-billion-dollar assets like the Mars Reconnaissance Orbiter do not drift into oblivion. This suggests a scenario of minimalistic endurance, a nightlight mode, where only the most fundamental data collection schedules, perhaps those pre-programmed and related to spacecraft safety and data legacy, are passively executed. Yet, does the silent, automated ticking of a clock truly constitute a vigilant watch, or does it merely create an illusion of presence while the opportunity for dynamic, responsive science slips away into the void? Simultaneously, and with impeccable timing, the European Space Agency has confirmed that its Martian Sentinels, Mars Express, and the Trace Gas Orbiter will actively observe 3I Atlas from October 1st to the 7th. Their sophisticated suites of instruments, the high-resolution stereo camera, the color and stereo surface imaging system, and a battery of spectrometers like Omega and Nomad are poised to dissect the light from this visitor, searching for spectral fingerprints that whisper of its composition and history. This clear declaration positions ESA not as a backup, but as the vanguard, ready to seize the lead role in this unprecedented observational campaign. The bureaucratic paralysis of one nation thereby creates a vacuum of leadership, into which another agency gracefully steps, transforming its orbiters into the primary eyes upon which the world's scientific community will rely. But can a single perspective, however sharp, ever capture the full, multidimensional truth of a cosmic mystery? This bifurcation of capability naturally gives rise to a more daring, cooperative hypothesis. Beyond the simple handoff of responsibility lies the potential for a clandestine, improvised partnership, a field operation mode, activated in the shadow of the shutdown. One can envision a shared real-time target-pointing network, a digital handshake between mission control in Darmstadt and the essential personnel maintaining the fort in Houston. In this scenario, the observational blind spots of one agency's orbiters are filled by the others, weaving a near-continuous chain of data points as Mars rotates, creating a planetary-scale observatory dedicated to a single, transient target. This would be a testament to the resilience of scientific internationalism, a silent agreement that transcends terrestrial politics. What protocols, then, would need to be silently bypassed, and what trust forged to enable such a seamless, real-time dance of machinery across the interplanetary stage? Yet, the most profound and speculative possibility pushes the boundaries of our operational imagination. We might contemplate the activation of a temporary, interplanetary watch station, with Mars itself serving as the central hub. Data, captured by the European orbiters, could be routed not through a single, potentially compromised network, but through a redundant, ad hoc pathway bouncing from the ESA ground stations to the dormant but alive Deep Space Network antennas, piecing together a live stream of the interstellar encounter. This would not be mere observation, it would be the construction of a real-time cinematic narrative of 3I Atlas's passage, a collective human effort to document a story that began light years away. Is it within our grasp to so fluidly retask our celestial infrastructure, to transform the rigid architecture of space exploration into a living, responsive nervous system for a single, transcendent purpose? Thus, the American shutdown inadvertently sets the stage for a grand demonstration of European capability and the latent endurance of NASA's minimalist systems, creating a potent precedent for emergency cooperation that may well define our response to the next unannounced guest from the galactic dark. And as the final data packets are downlinked from this coordinated vigil, a more fundamental question about the visitor itself begins to take shape, its trajectory pointing back toward its enigmatic origins. For the vector of 3I Atlas, This super-hyperbolic arc that slices so near the Martian sphere carries it onward to its perihelion on October 29th. 2025, a trajectory that is itself a cryptic message from the void. What secrets of its extrasolar genesis are encoded in the precise geometry of this celestial slingshot? And what does its unwavering path through our system reveal about the dynamical motorways of the galaxy? Against the silent, star-dusted backdrop of the ecliptic plane, the fundamental stage upon which the planets of our solar system perform their eternal, graceful dance, a solitary traveler now makes its entrance. Its trajectory, a stark and unwavering line against this cosmic floor, is not a gentle curve of belonging, but a decisive, hyperbola-shaped scar, a vector of pure velocity. This is 3I Atlas, the third interstellar object ever confirmed to be passing through our realm, a celestial nomad whose very path is its only credential. According to the meticulous calculations of the European Space Agency, this visitor was first sighted on the 1st of July, 2025, by the vigilant eyes of the Atlas network in Hawaii, Chile, and South Africa, a system designed to warn of inbound dangers, now revealing an inbound mystery. It glided past the orbit of Mars in early October at a distance of a mere 0.19 astronomical units, a silent witness to the red planet's solitude, before continuing its relentless plunge towards a perihelion rendezvous with our Sun on the 29th of October. This trajectory, so improbably flat and aligned with our solar system's own architectural blueprint, is the first and most profound clue to its origin. Could it be that this path, so parallel to our own planetary disk, is a deliberate signature, a universal constant indicating that the visitor hails from a star system whose planetary children were spun from a similarly flattened protoplanetary disk? The sheer velocity of 3I Atlas, a breathtaking 210,000 kilometers per hour, speaks of a violent birth, an expulsion of unimaginable force from its native system. The mainstream scientific explanation posits a gravitational drama on a cosmic scale. Perhaps this object was a mere pebble in the chaotic environment of a dense star cluster, subjected to a series of gravitational slingshots by passing stellar giants, each interaction adding momentum until it reached escape velocity. Alternatively, it could be a youthful fragment, a piece of primordial ice and dust recently hurled out from the tumultuous disk of an infant star, a system still in the throes of planetary formation. Yet, its survival of such a cataclysmic ejection, and now its approach to the ferocious heat of our Sun, suggests a more resilient constitution. This leads to a more speculative hypothesis. What if 3I Atlas is not a simple rubble pile or a fragile icy aggregate, but possesses an anomalously high fraction of refractory materials, a solid core of rock and metal, forged in the inner furnace of its home star, a hardy survivor, built to endure the long, cold journey between the stars? If it is indeed such a resilient wanderer, what secrets of planetary core formation, from a system we may never see, are locked within its darkened heart? To truly decipher its story, we must engage in a layered analysis, peeling back the narrative of its journey. The first level of inquiry is its flat orbital geometry, a characteristic that strongly suggests an origin within the thin disk of a star system, not unlike our own, a place where the fundamental laws of angular momentum have sculpted a familiar architecture. This provides a context, a potential home, but not the mechanism of its departure. Ascending to the second level, we confront its extreme eccentricity and formidable speed, which demand a more dynamic and violent explanation, a close gravitational encounter with a giant planet, or perhaps a binary star system, an event so powerful it not only ejected the object, but may have scorched its surface, creating a thermal shock layer that could now, as it approaches our Sun, trigger unexpected and volatile outgassing activity. But the most profound clue may lie at the third and most subtle level of analysis, the object's rotation. The specific pattern of dust in its developing tail, a direct consequence of its initial angular momentum, acts as a cosmic gyroscope, a frozen record of its rotational state. This spin is not arbitrary. It is the sum of all the torques and impacts it experienced before its final ejection. Could it be that the precise wobble and precession of 3I Atlas are in fact an encrypted logbook detailing the very collisions and gravitational jostling that culminated in its exile from its home system? The implications of this analysis extend far beyond the classification of a single curious object. Tracing the dynamical history of 3I Atlas could be the key that unlocks our understanding of a hidden population of interstellar drifters, a vast archipelago of frozen worlds and rocky fragments wandering the galactic voids. Each one is a natural sample, a time capsule, holding the unaltered chemical and physical conditions of a young planetary system, offering a comparative planetology that we could never achieve by studying our solar system alone. By reading its trajectory, its composition, and its spin, we are not merely studying a visitor, we are attempting to read a single page from the vast, distributed library of the galaxy's planetary history. But to truly read this page, we must first capture its most volatile chapter, the moment of its greatest transformation, which is now swiftly approaching. And so, as this interstellar messenger begins its fiery dive towards the sun, a state of quiet emergency is declared across the scientific world. The European Space Agency has placed its Mars Express and Trace Gas Orbiter, already in position around the Red Planet, on high alert, ready to capture every possible datum as the object recedes from its Martian passage. Across the Atlantic, even amidst the bureaucratic silence of a government shutdown, NASA maintains a skeleton crew for essential operations, a testament to the profound importance of this opportunity. They cannot afford to miss this singular, historical moment, the brief window before 3I Atlas plunges into the solar furnace and potentially alters its fundamental nature forever. For what truths, currently frozen in its ancient interior, will be vaporized into its temporary atmosphere, only to be lost to the void just as we learn to see them? In the silent, airless theaters of space, where government proclamations hold no sway over the trajectories of celestial bodies, a unique form of emergency has been declared. On Earth, the machinery of human governance may stutter and halt, its budgets frozen and its non-essential functions suspended. Yet, in the profound quietude of Martian orbit, the electronic eyes and sensitive noses of our mechanical emissaries remain wide awake. The European Space Agency's Mars Express and Trace Gas Orbiter have been placed on a state of high alert, their observational schedules meticulously cleared for a critical window, while across the Atlantic, NASA maintains its essential deep space network operations, a testament to the notion that some infrastructures transcend terrestrial politics. This is not a drill for a planetary storm or a geological upheaval. It is a vigil for a visitor. As the object known as 3I prepares for its perihelion passage, intensifying in activity as it draws nearer to the sun's furnace, a coalition of the willing and the operational has assembled its instruments, ensuring that a historical moment is not lost to a terrestrial shutdown. For when human budgets pause, the telescopes, in their eternal vigil, must remain open. According to the public bulletins from the European Space Agency, the frames of October 1st to 7th have been deliberately emptied for the Mars Express and the Trace Gas Orbiter, with a specific emphasis on instruments like the HRSC, CASES, and, most tellingly, the suite of spectrometers, Omega, SpyCam, and the highly sophisticated Nomad. Concurrently, NASA's contingency plans for a government shutdown explicitly categorize the operation of satellites and the maintenance of data downlink capabilities as accepted activities, critical for the protection of agency assets, and the continued function of international partnerships such as the International Space Station. This suggests a deliberate, coordinated pivot. The primary observational payload is shifting from high-resolution images to remote sensing spectrometers, from seeing to, essentially, smelling. NASA, in turn, prioritizes the data pipeline itself, treating its deep space network as a public utility that must flow uninterrupted, even when other services cease. One cannot help but observe the emergence of a de facto, if not publicly announced, joint ESA-NASA coordination panel, a ghost in the machine orchestrating this silent symphony from two continents momentarily divided by a fiscal impasse. Could this be the nascent prototype of a planetary-scale emergency response protocol, activated not by a formal treaty, but by the sheer, undeniable significance of the celestial event unfolding before us? At its most fundamental level, this vigil appears as a simple, low-risk data collection exercise. The initial hypothesis, Level 1, posits a sparse and distributed observation campaign, a series of discrete snapshots and spectral readings designed to minimally impact the spacecraft's other scientific duties while capturing the broad strokes of Three Eyes evolution. The risk is negligible, the schedule thin. Yet, as the object's brightness is predicted to surge in its solar approach, the mission parameters appear to escalate in ambition. We enter Level 2, a transition from periodic imaging to near-continuous spectroscopic monitoring. The instruments are not merely taking pictures, they are dissecting light, hunting for the faintest spectral fingerprints of outgassing molecules, water, carbon dioxide, cyanogen that the Nomad instrument is exquisitely tuned to detect across vast distances. This is no longer passive observation, it is an active chemical interrogation of the visitor. But what if even this heightened state of vigilance is merely a prelude? What unseen script are the mission controllers preparing to follow? This leads us to the precipice of a truly speculative Level 3 hypothesis, the activation of a transplanetary synchronized campaign. Imagine the data stream from the Martian orbiters, a river of digital insight, being routed not only to Earth but also backwards, through the European Space Agency's Deep Space Relay architecture, to be seamlessly integrated with the concurrent observations of the James Webb and Hubble Space Telescopes. When the celestial geometry permits a simultaneous line of sight, a unified multi-point sensor net would be cast across the inner solar system. This would allow for the construction of an unprecedented chronological sequence, an hourly map of the evaporation rates and chemical evolution of Three Eyes coma as it is heated by the Sunday. We would no longer be looking at a solitary object from a single vantage point, but witnessing a dynamic process unfold in 3 dimensions and in real time. Is humanity in its fragmented state unconsciously assembling the first true nervous system for perceiving interstellar phenomena, a distributed consciousness aimed at the unknown? The ultimate impact of this unplanned drill may therefore not be the data on 3i alone, but the creation of a new operational paradigm. In the shadow of a government shutdown, an interagency emergency mode has been born, a proof of concept for a future where interstellar guests do not announce their arrivals. This ad hoc coalition, forged in the fires of fiscal limitation and scientific necessity, may well become the template for an age of unannounced celestial diplomacy. It demonstrates that our curiosity, our drive to comprehend the cosmos, can itself become a critical infrastructure, as vital as any power grid or communication network. And as we perfect this new mode of seeing, of smelling from afar, what other secrets might we be preparing to unveil, just as our instruments detect the first curious hints of an anomalous, sunward-directed dust ejection from the visitor's core? In the silent, perpetual night of the interplanetary void, celestial mechanics dictates a predictable ballet. A comet, that ancient vagabond of ice and dust, approaches the inner solar system, and the solar wind, that relentless exhalation of our star, sculpts its ephemeral atmosphere into a magnificent, incandescent tail that always streams away from the Sunday. It is a fundamental tenet of cometary science, a rule as seemingly immutable as the orbits of the planets themselves. Yet, in the late summer of 2025, this rule was broken. A solitary wanderer, observed with the full arsenal of modern astronomy, presented a spectacle that defied this most basic expectation. Its dust tail, a faint but unmistakable brushstroke against the cosmic canvas, was seen pointing not away from, but toward, the brilliant fury of our day star. When a dust tail turns its face to the sun, the classical rules of cometary behavior begin to falter, inviting us to question the very foundations of our understanding of these primordial objects. The initial and most conservative explanation for such a perplexing orientation lies in the fundamental physics of the particles themselves. According to current models, the behavior of cometary dust is a delicate dance between two opposing forces: the outward pressure of solar radiation, which pushes minute particles away, and the gravitational pull of the sun, which seeks to retain them. Scientists suggest this could be due to a population of unusually large and massive dust grains ejected from the nucleus. These substantial fragments, possessing significant momentum, would be far less susceptible to the gentle but persistent push of radiation pressure, allowing the sun's gravity to dominate their trajectory and curve their paths sunward, creating the illusion, or perhaps the reality, of a retrograde tail. The initial data from the James Webb Space Telescope spectroscopic instruments seem to corroborate this, revealing a complex coma rich not only in water vapor, but in CO2 and CO, hinting at a violent outburst that could have excavated and lofted such coarse, dense material from the comet's interior. But that elegant solution does not fully account for the tail's coherent structure, a singular defiant gesture rather than a diffuse cloud of gravitationally bound debris. If these were merely heavy particles succumbing to gravity, why would they organize themselves into a tail-like feature with such apparent directionality, a stark contradiction to the pristine, sun-opposing ion tail that was also present? This anomaly compels us to consider a more dynamic and localized phenomenon. Could it be that we are witnessing not a general property of the dust, but a specific, transient event? A powerful, localized jet erupting from a fissure on the nucleus that was, by a quirk of rotational geometry, cast into permanent shadow, a volcanic vent hidden from the solar wind's direct influence. Such a jet, unmoderated by the usual outgassing forces, might project material ballistically, its trajectory dictated solely by the nucleus's rotation and its own initial velocity, potentially creating a temporary sunward-pointing streamer. And if this jet were located near one of the nucleus's poles, the complex interplay of rotational forces could further torque and redirect the ejection, weaving a thread of dust back toward the light. Is the universe presenting us with a celestial sleight of hand, where a simple shadow can rewrite the direction of a comet's signature? The European Space Agency, in its preliminary analysis, has been characteristically meticulous, noting the confirmed presence of standard cometary volatiles H2O, CO2, CO within the coma, as detected by both the Hubble and the James Webb Space Telescopes. Yet, they simultaneously emphasize a critical and often deceptive variable: the critical role of phase angle geometry and overall brightness in determining the quality and interpretability of the images. Instruments like the high-resolution stereo camera, HRSC, and the Cassis camera, designed for planetary observation, were only expected to resolve a clear cometary halo or tail at a much closer approach, perhaps within 30 million kilometers. The fact that this anomalous feature was discernible at all speaks to its unusual intensity, but it also opens the door to a third, more illusory possibility. Could this entire phenomenon be a phantom of perspective, a complex phase angle illusion where the three-dimensional geometry of the comet's coma and its various dust features when projected onto the two-dimensional plane of our detectors, conspires to create the convincing image of a sunward tail where none truly exists. What if our instruments, for all their precision, are merely tracing the shadow of a deeper, more complex structure we have yet to comprehend? This line of inquiry naturally elevates the analysis to a higher level of complexity, moving beyond simple particle dynamics or observational artifacts. If we dismiss the illusion hypothesis and accept the tail's orientation as a genuine physical reality, we must consider the first escalation: that this tail deviation is the product of a rapidly rotating nucleus, punctuated by powerful, asymmetric local jets. A comet spinning with sufficient velocity could, in principle, act like a celestial lawn sprinkler, its jets of gas and dust whipping around its axis with such speed that the material from a single eruption is smeared across a wide arc, some of it even thrown backward against the prevailing solar wind. The timing and location of these eruptions become a critical, chaotic factor, capable of producing transient and seemingly paradoxical structures. But what underlying mechanism could generate such violent and focused outbursts on a body often thought of as a loosely consolidated, dirty snowball? This leads us to the second escalation, a hypothesis that probes the very nature of the cometary surface. Perhaps the lopsided tail is not an aberration, but a symptom. It could be the result of a bizarre surface phase, mixture of ice and dust, a crust with strange thermodynamic properties, perhaps laced with supervolatile ices or complex organic polymers. Such a surface could absorb solar energy in a non-uniform manner, building up immense pressure in subsurface cavities until it releases its pent-up energy in a cyclical, geyser-like eruption. This would not be a single jet, but a series of programmed outbursts, each one spraying material in a preferred direction dictated by the local topography, potentially weaving the dust into a twisted, helical tail that, from our specific vantage point, presents a segment pointing ominously sunward. Are we witnessing the seasonal, clockwork respiration of a comet whose internal chemistry is far more complex and active than we ever imagined? And if we dare to venture further, into the realm of the truly speculative, we arrive at the third and most profound escalation. What if the dust itself is not inert? The data indicates an unusually high albedo in certain wavelengths, a reflectivity that could hint at a composition rich in metallic particles. Imagine, for a moment, that this comet's nucleus is seeded with fine, ferromagnetic dust, tiny fragments of iron or nickel, remnants from a primordial solar nebula that was far more magnetically active. Upon being liberated from the nucleus, these particles would no longer be simple pawns of gravity and light. They would become charged, susceptible to the invisible currents of the interplanetary magnetic field, which is itself carried outward by the solar wind. Under the right conditions, this magnetic field could act as a cosmic shepherd, gathering these metallic grains and pulling them along its own lines of force, which can be twisted and contorted by solar activity into configurations that do not always point radially away from the Sunday. The tail, then, would not be a windsock, but a tracer of magnetic flux, a visible record of an invisible force, flowing against the stream of photons. Could it be that we are not looking at a dust tail at all, but are instead granted a rare glimpse into the magnetic architecture of our solar system, painted in the faint glitter of ancient metal? The implications of this phenomenon, regardless of its ultimate cause, ripple outward from this single anomalous comet and touch upon one of the most pragmatic endeavors of modern space science: planetary defense. If the dominant explanation proves to be the prevalence of heavy particles, then our fundamental models of cometary mass loss require immediate and significant revision. These models are the bedrock upon which we can sit here, predict a comet's brightness, its tail development, and most critically, its non-gravitational orbital perturbations, the subtle, jet-induced pushes that can alter its path over time. An unaccounted-for propensity to eject large, massive grains would mean our predictions for how a potentially hazardous object evolves as it approaches the inner solar system are inherently flawed. A comet that behaves according to this new, observed logic could arrive brighter or fainter, or on a slightly different trajectory than our best simulations forecast. Does this single, sunward-pointing tail, therefore, represent not just a curiosity, but a subtle warning that our maps of the celestial dangers lurking in the dark may be missing critical and potentially consequential details? As the collective gaze of the world's observatories remains fixed upon this celestial rebel, each new data point refines the puzzle without yet offering a definitive solution. The dance of hypotheses continues, from ballistic mechanics to rotational dynamics, from photometric illusions to magnetic phantoms. Each seems to hold a fragment of the truth, yet none completely captures the elegant perversity of a tale that dares to look into the Sunday. The next step in unraveling this mystery lies not in the ethereal tales, but in the solid heart of the object itself. To understand the source of the aberration, we must turn our focus to the nucleus, the fount from which all these mysteries flow. Current estimates, derived from its brightness and thermal signature, place its diameter somewhere between a modest 0.32 to a substantial 5.6 kilometers, a significant range of uncertainty for an object of such interest. This variance itself hints at an irregular, potentially fragmented geometry that could be the key to its strange behavior. And so, the question now presented to the instruments of humankind is one of resolution and proximity. Can the powerful eye of HiRISE aboard the Mars Reconnaissance Orbiter, as it prepares for a fortuitous and relatively close pass, achieve what other telescopes cannot? Can it pierce the veil of the coma and resolve the intricate, irregular geometry of this enigmatic nucleus during this fleeting encounter? In the silent, sun-illuminated void between the orbits of Mars and Jupiter, a solitary sentinel, the Mars Reconnaissance Orbiter, turns its gaze away from the rust-colored plains below. Its formidable eye, the high-resolution imaging science experiment, or HiRISE, capable of discerning a dinner table from 300 kilometers away, is tasked with a pursuit of an entirely different magnitude. Its target is not the familiar geology of the red planet, but a fleeting, enigmatic visitor from the interstellar depths, the object known as 3I Atlas. The challenge is one of cosmic scale and profound technical audacity. Can an instrument designed to map the intricate canyons of another world truly capture the elusive, the irregular geometry of a celestial wanderer, estimated to be a mere speck of between 0.32 and 5.6 kilometers in diameter, as it streaks past at a staggering distance of 30 million kilometers? The very proposition pushes the boundaries of our observational prowess, forcing us to confront the limits of our vision in the immense theatre of the cosmos. The HiRISE camera is, without hyperbole, a masterpiece of optical engineering. From its orbital perch approximately 300 kilometers above Mars, it achieves a resolution of about 0.3 meters per pixel, a feat equivalent to reading a newspaper headline from a distance of several city blocks. This staggering acuity is quantified by its instantaneous field of view, a mere 1 microradian. This unit of angular measurement, 1/millionth of a radian, defines the sharpest point of its vision. Yet, when we transpose this same exquisite 1 microradian resolution to the yawning chasm of 30 million kilometers that separates MRO from the interstellar interloper, the mathematics of perspective delivers a sobering result. At such an astronomical range, that single sharp microradian translates to a blurry 30 kilometers per pixel. The entire nucleus of 3I Atlas, even at its most generous estimated size, would occupy less than 1/30th of a single pixel in HiRISE's detector. It would be a submicroscopic point, a data ghost, its form utterly dissolved into the digital noise. This is not a limitation of the technology, but an immutable law of physics, a consequence of the inverse square law and the fundamental wave nature of light itself. The European Space Agency, in its own assessments, has corroborated this stark reality, noting that 3I Atlas at this distance would indeed be smaller than a single pixel, and that any observation would be of its extended coma and tail, not its core. Given these unassailable physical constraints, what possible configurations could the light captured by HiRISE take, and what truths might they, in their ambiguity, still conceal? We are thus presented with a spectrum of potential outcomes, each a narrative in its own right. The first, a triumphant scenario, would be that HiRISE, against all odds, captures the nucleus itself, a key titch, a miracle. This would imply either a catastrophic and luminous outburst of activity from the nucleus, temporarily inflating its apparent size, or a fundamental miscalculation in our initial size estimates, suggesting an object of far greater and more substantial dimensions. The second, more probable outcome is that HiRISE sees not a point, but a faint, diffuse smudge, a fin star, the comet's coma. This ethereal halo of gas and dust, illuminated by the distant sun, would be a luminous cloud without a discernible center, a beacon announcing the object's presence while guarding the secret of its solid heart. The third, and most minimalist result, would be a single, saturated pixel, a brilliant, overexposed dot of pure light, containing no morphological information whatsoever, a stark testament to the object's immense distance and minuscule angular size. It would be a confirmation of presence, but a denial of identity. So, if the nucleus remains perpetually out of focus, a ghost in the machine, what alternative methods can we employ to tease its secrets from the void? This impasse forces a fundamental and elegant recalibration of the mission's scientific objectives. The role of MRO and HiRISE must transform from that of a cosmic cartographer to that of a meticulous photometrist. If the geometry of the nucleus is forever beyond our grasp, its behavior in time is not. By conducting a prolonged campaign of observations, carefully measuring the minute fluctuations in the object's total brightness, scientists can decipher the rhythmic pulse of the comet's rotation. As the irregular nucleus spins, its cross-sectional area and surface albedo change, creating a subtle repeating light curve. This cadence, this celestial heartbeat, can be extracted even from a featureless point of light. The data would provide a direct measurement of the rotation period, a fundamental physical property that holds clues to the object's internal strength, its mass distribution, and the torques exerted upon it by outgassing jets. This photometric data, when combined with simultaneous observations from other great observatories, would become the golden data for constraining sophisticated models of dust, physics, and cometry activity. But can we push our analytical ingenuity even further to somehow reconstruct a shadow of the form we cannot directly see? The pursuit of knowledge, when faced with a wall, does not halt. It seeks a ladder. The first rung on this ladder is a technique as pragmatic as it is powerful, trailing and stacking. By tracking the motion of the comet across the starfield and stacking multiple short exposure images, the faint signal of the coma and tail can be amplified, while the random noise of the detector is averaged out. This would allow for a detailed study of the comet's activity, the structure of its tail, the symmetry of its coma, potential jets offering indirect clues about the nature of the hidden nucleus. The second, more advanced rung involves leveraging the unique orbital platform of MRO itself. Could one not, in a feat of computational virtuosity, employ a form of interferometry, not with multiple telescopes, but with multiple orbital positions of the same telescope? By capturing images from different points along the MRO's orbit around Mars, one could, in theory, synthesize a virtual telescope with a baseline of thousands of kilometers. This supersynthetic telescope would possess a resolution far exceeding that of HiRISE's physical aperture, potentially allowing it to resolve details of the nucleus that were previously thought to be irretrievably lost. This is, for now, a speculative leap, a whisper at the frontier of observational technique. Yet, if such a thing were possible, what profound revelation might emerge from the synthesized data? Could the first, blurry outline of an interstellar heart be revealed? Thus, even in the anticipated absence of a clear image, the endeavor is far from a failure. The very attempt to train a Martian eye upon an interstellar visitor is a testament to our species' relentless curiosity. The photometric light curve, the detailed analysis of the coma's spectrum and morphology, these are the precious, hard-won treasures from this cosmic rendezvous. They are the data points that will feed the models, constrain the theories, and inch us closer to understanding the true nature of these nomadic worlds. The nucleus may remain shrouded, a silhouette against the starfield, but its dynamic shadow play will speak volumes. For if we cannot see the sculptor, can we not still learn of its craft by studying the shape of the dust it throws into the solar wind? And as this ephemeral traveler continues its hyperbolic arc through our inner solar system, its origin, the story beckons with even greater allure. It arrived from the direction of the constellation Sagittarius, a realm not of random stars, but of the galactic center itself, a dense, dynamic, and violent region of space. Its hyperbolic excess velocity, a speed too great to be bound by the sun's gravity, marks it as a true interstellar vagabond. This trajectory is not merely a direction, it is a clue etched in celestial dynamics, a pointer back to a birthplace we can only imagine. Was it, in the distant past, a silent, frozen entity in a nascent planetary system, violently ejected by the gravitational machinations of a giant planet, cast adrift to wander the void between stars? Or does its origin point to an even more exotic cradle, a dense stellar nursery near the galactic core, where the chaotic ballet of young stars and the gravitational tides of the central supermassive black hole itself can easily fling debris out into the galactic halo? Its incredible speed suggests it has felt the pull of immense gravitational forces, a slingshot effect on a scale we can scarcely comprehend. Could it be a fragment from a protoplanetary disk around a star that has since died or migrated? A pristine relic from a creation process that occurred in an environment utterly unlike our own quiet stellar neighborhood? The data from HiRISE, even indirect, will begin to answer these questions, but the ultimate mystery of its genesis remains. What cataclysmic event, in the dense starfields near the heart of the Milky Way, could have imparted such velocity upon this fragment of ice and rock, setting it on a billion-year journey that would, for a fleeting moment, bring it within the observational reach of a species on a pale blue dot, forever asking, from what forgotten shore did this messenger arrive? From the silent, star-drenched depths of the constellation Sagittarius, it emerged a solitary voyager on a trajectory that spoke of a profound and violent past. The object designated 3I Atlas did not simply enter our inner solar system. It arrived as a messenger, a cipher etched in ice and dust, its very path a line pointing unerringly back towards the heart of our galaxy. This was not a random drift through the interstellar void. It was a purposeful, if unconscious, arrow shot from the cosmic forge itself, a trajectory that invites us to trace a line backward along its path. A reverse fingerprint leading toward the bustling, chaotic nursery of stars and planets that huddle near the galactic core. Its immense velocity, a staggering 210,000 kilometers per hour, as confirmed by the meticulous tracking of the European Space Agency, was not merely a number on a screen, but a testament to forces far exceeding the gentle tug of our own sun's gravity, a kinetic signature of an origin steeped in gravitational tumult. This speed, this specific bearing from a region of such stellar density, presents us with our first, fundamental dichotomy. Was this a fragment casually discarded from a crowded stellar neighborhood? Or was it a projectile violently ejected from the very cradle of planetary birth? The mainstream scientific narrative, grounded in the well-understood dynamics of celestial mechanics, offers a compelling initial explanation. Within the dense stellar clusters that populate the galactic bulge, or in the sprawling gravitational influence of a young, active star, such velocities are not only possible but expected. One hypothesis suggests that 3I Atlas could be a remnant, a piece of primordial debris cast out from a densely packed star system, its journey beginning with a series of intricate gravitational dances. In this scenario, a cascade of close encounters with larger bodies, a series of cosmic slingshots could have progressively accelerated the object, imparting upon it the tremendous velocity we now observe, effectively making it a gravitational billiard ball shot out into the dark. Another, equally plausible theory posits an origin within a volatile protoplanetary disk of a young star, a region rich in the volatile ices observed in its coma. Here, gravitational instabilities during the planet-forming process could have catapulted this fragment clear of its stellar parent's grip, sentencing it to an eternity of cold wandering. These are elegant, rational models, built upon the solid foundation of Newtonian and Keplerian laws, explaining both the object's speed and its composition through known, if extreme, astrophysical processes. Yet, does the sheer specificity of its origin point, its unwavering line from the galactic center, a place of unimaginable scale and energy, fully acquiesce to such straightforward interpretations? The initial velocity required to achieve its current state, after eons of travel through the dissipative medium of the interstellar medium, must have been truly prodigious, perhaps pointing to a single, cataclysmic event rather than a series of gentle nudges. Could its journey have begun not in a common cluster, but in the chaotic debris field surrounding a rogue star, a stellar outcast itself flung from the galactic core, carrying with it the raw materials of its own brief system? Or perhaps, more speculatively, the gravitational assist it received was not from a series of planets, but from a single, dense, and dark companion, a neutron star, or even a stellar mass black hole, whose immense gravity could, in one fleeting encounter, impart such a ferocious kick. The velocity itself becomes a question, not just an answer, a signature of an environment far more extreme than our models typically account for. The chemical analysis, conducted by the most powerful eyes we have trained upon the heavens, the James Webb Space Telescope and the Hubble Space Telescope, adds a rich, complex layer to this mystery. They detected the faint but distinct coma of 3I Atlas, a tenuous atmosphere betraying the presence of water vapor, carbon dioxide, and carbon monoxide, as it was warmed by our Sunday. At the first level of analysis, this composition appears comfortingly familiar, a near-perfect match to the volatile profiles of many comets native to our own solar system. This similarity suggests a universal commonality in the planet-forming process, a standard recipe of ices that condenses in the cold outer regions of any nascent stellar system. It implies that the building blocks of worlds, the water for oceans, the carbon for life, are not unique to our own cosmic neighborhood, but are a fundamental ingredient scattered throughout the galaxy. This finding reinforces the Copernican principle, the idea that there is nothing inherently special about our position or our composition in the universe. But a deeper, second level of scrutiny reveals subtle, yet potentially critical deviations. The ratios of these ices, the precise abundance of carbon monoxide relative to water, or the trace signatures of more complex molecules, do not align perfectly with any single class of solar system comet. These are the subtle fingerprints, the isotopic and molecular quirks, that serve as a forensic record of the specific environmental conditions in which this object formed. The temperature of the protoplanetary disk, the intensity of the young star's ultraviolet radiation, the density of the cosmic rays it was exposed to over billions of years, all these factors leave an indelible mark upon its chemical soul. The anomalous ratios are thus a cryptic message, a clue to the specific pressure and temperature conditions of its home system, conditions that may have been radically different from our own. They hint at a stellar parent of a different spectral class, or a formation location within its disk that has no direct analogue in our familiar solar architecture. And this leads us to a third, profoundly speculative level of inquiry, a frontier where science bleeds into the theoretical sublime. What if, locked within the atomic structure of its dust grains, are isotopic, anomalies so strange and so distinct that they act not merely as an environmental clue, but as a precise coordinate? Imagine that the ratios of certain isotopes, oxygen, nitrogen, hydrogen, form a pattern so unique, so statistically improbable to have arisen independently, that it functions as a veritable barcode, a chemical signature, pointing directly to its stellar system of origin. We could, in theory, scan the galactic center with future spectroscopic instruments, searching for a star whose own photospheric absorption lines bear this same unique isotopic imprint. The object would then transform from a mere wanderer into a named emissary, its provenance known, its journey mapped not just geometrically, but genetically. But what natural process could create such a stark, unambiguous signature across light years of space? And are we, in our search for patterns, merely seeing a cosmic cartography where none was intended? The implications of confirming such a hypothesis are monumental, extending far beyond the academic satisfaction of solving a single puzzle. If 3I Atlas is indeed a pristine sample from a fully alien planetary system, then it becomes the first tangible, physical standard for comparison. It is a reference specimen from a laboratory we have never visited, a control for our understanding of cosmochemistry. This realization gives urgent, profound purpose to nascent mission concepts like the European Space Agency's Comet Interceptor, a mission designed to lie in wait for the next such opportunity. To successfully rendezvous with and analyze such an object would be to hold in our hands, quite literally, the building blocks of another world. It would provide the ground truth against which all our remote observations of exoplanetary atmospheres and disks could be calibrated. But are we, as a species and a scientific community, truly prepared for the knowledge that might be unlocked from a fragment of another star's family? And what fundamental truths about our own solitude or ubiquity might it irrevocably shatter? Its passage through our celestial neighborhood is as brief as it is illuminating, a fleeting visit that demands an unprecedented campaign of observation. Its trajectory is now a known quantity, a precise celestial itinerary. It will swing past our sun at perihelion on the 29th of October, a blistering close encounter that will violently stir its frozen guts, before gliding past the cloud-shrouded sphere of Venus on the 3rd of November. Its journey will then bring it to its closest approach to Earth on the 19th of December, a distant but profoundly significant pass at 1.8 astronomical units, before its long arc carries it out towards the gravitational domain of Jupiter in early 2026. This path presents a series of unique observational windows, opportunities to study the object's changing activity and structure under varying solar influences. Yet, this celestial schedule begs a critical, logistical question. In this brief window of opportunity, can the fleets of robotic explorers we have stationed around Mars and the planned orbital assets at Jupiter be mobilized and their missions reprioritized to conduct a continuous, coordinated vigil? Can our mechanical sentinels, designed for local studies, pivot their gaze to track this interstellar passerby, creating a multi-point baseline of data that would be impossible to gather from Earth alone? The answer hinges not on capability, but on will and coordination, a test of our agility in the face of the cosmos's unpredictable offerings. For as it continues on its predetermined path, swinging past the inner planets and setting its sights on the gas giant realm, one must wonder what further secrets will be revealed when it enters the gravitational sphere of Jupiter, a domain whose immense pull has been known to capture and alter the fates of countless smaller bodies. Will the subtle perturbations of its path by the giant planet's gravity reveal new details about its mass and density, clues to its internal structure hidden until now? And as it passes this final checkpoint within our system, its coma potentially rejuvenated by its journey around our sun, what final transmission of data will it offer before it recedes once more into the silent, star-flecked darkness from whence it came, leaving behind only a trail of transformed questions? Of course. Here is the script, crafted in the requested style. The inner solar system, for all its perceived clockwork regularity, is not a static tableau. It is a dynamic arena, a cosmic highway where gravitational forces sculpt ceaselessly and silent voyages commence in the profound darkness between worlds. We have mapped the orbits of countless asteroids and comets, charting their predictable paths through the ecliptic plane, yet we remain ever vigilant for the anomaly, the object whose trajectory whispers of origins beyond our familiar celestial neighborhood. The arrival of such a visitor, designated 3I Atlas, has not merely piqued scientific curiosity, it has presented a logistical and philosophical challenge of unprecedented scale. Its projected path is not a simple parabolic arc into the inner system and back out again. It is a grand tour, a meticulously plotted sequence of gravitational handshakes that will see it graze the inner planets in rapid succession. A perihelion passage on the 29th of October, a swift, elegant glide past the cloud-shrouded sphere of Venus on the 3rd of November, and finally, the approach to our own world on the 19th of December, a silent pass at a distant but significant 1.8 AU, before its momentum carries it outward, towards the gravitational dominion of Jupiter in the early days of 2026. This celestial itinerary presents a profound question to the scattered robotic sentinels we have placed across this system. Can we, the inhabitants of a single planet, muster a coordinated vigil, a seamless chain of observation, from the rust-coloured plains of Mars to the swirling gas giant and its icy moons? Can we arrange the shift work from Mars to Jupiter in time to witness this entire performance? The immediate, pragmatic response from the various space agencies is one of controlled urgency, a symphony of repurposed missions and recalibrated instruments. According to current models and announced plans, the European Space Agency has already tasked its veteran Mars Express and the more recent Trace Gas Orbiter with a dedicated observing campaign from the 1st to the 7th of October, their unique vantage point from Martian orbit offering a critical first look as the object begins its inward plunge. The baton would then, in theory, be passed to the Jupiter Icy Moons Explorer, JUICE, which, though still en route to its final destination, is scheduled to attempt preliminary observations in November of 2025. Yet, the vast gulf of space introduces a profound delay. The data from this maneuver, a whisper from the outer darkness, will not trickle back to Earth until approximately February of 2026, long after the object has passed its closest point to the Sunday. To bridge this temporal and spatial chasm, ESA is reportedly considering an unprecedented collaboration with NASA's Europa Clipper, leveraging their twin ultraviolet spectrometers to create a stereo view, a form of cosmic triangulation that could reveal secrets of the object's composition and activity. Even missions with other primary objectives, such as the Psyche spacecraft, en route to its metallic namesake asteroid and the Lunar Reconnaissance Orbiter, are being evaluated for any possible geometric alignment that would allow for a fleeting, opportunistic glance. And when the object passes too close to the Sun's overwhelming glare for any planetary orbiter to safely observe, the entire network of solar observatories, such as the venerable SOHO, would become our collective eye, tracking this enigmatic visitor as it swings through the solar furnace. This constitutes a level of international and intermission coordination seldom attempted, a patchwork of pre-existing capabilities hastily woven into a nascent observational net. But is a patchwork, however ingenious, sufficient to comprehend a phenomenon that moves with such silent, determined purpose through the very fabric of our celestial backyard. This initial reactive approach can be considered the first level of our engagement, a sparse, distributed monitoring campaign where each spacecraft captures its own unique, temporally isolated window of data. Each platform, from Mars Express to JUICE, operates within its specific constraints of power, data bandwidth, and pointing accuracy, providing a series of snapshots, a light curve here, a spectral analysis there, like individual pages torn from a continuous narrative. The data would be invaluable, yet fundamentally discontinuous, a staccato rhythm of information against the legato flow of the object's journey. We would know its state at point A, and again at point B, but the critical transitions, the subtle changes in outgassing or rotation as it is heated by the sun and perturbed by planetary encounters, would have to be inferred, not directly observed. This method treats the solar system as a collection of discrete observation posts, not as a single, integrated instrument. Can a story told in fragments ever be truly understood, or does the essence of the narrative lie in the unobserved moments that connect them? The second, more sophisticated level of analysis would seek to weave these disparate threads into a coherent tapestry. It is not merely about collecting data, but about fusing it into a unified model. The true power of this distributed network would be realized not in the isolation of each dataset, but in their synthesis. The particle sensors aboard JUICE, designed to characterize the plasma environment of Jupiter, could be trained upon 3I Atlas, measuring the solar wind's interaction with its coma, and any charged particles it sheds. This information, when combined with the visual and spectroscopic data from the Mars orbiters and the potential ultraviolet observations from the Clipper-JUICE duo, would allow scientists to construct a multi-dimensional profile. We could move beyond simple imagery and begin to draft a dynamic activity curve, a chronicle of how this object breathes and changes in response to the intense solar radiation following its perihelion. We would be observing not just an object, but a process, a real-time experiment in celestial mechanics and chemistry. This represents a paradigm shift from passive observation to active, systemic interrogation. But does even this holistic view capture the full picture, or are we merely assembling a more detailed model of the Sphinx without ever hearing it speak? This leads us to the third, and for now, speculative level of engagement, the concept of an autonomous interplanetary astronomical network. Imagine a future where our robotic probes are not merely individual tools, but nodes in a conscious, self-organizing neural net spanning the solar system. An artificial intelligence, privy to the orbital mechanics and instrumental capabilities of every observatory, orbiter, and deep space probe, could dynamically allocate observation time, calculating optimal viewing geometries in real time to maintain a near-continuous vigil on a target like 3I Atlas. A gap in coverage from the Martian orbiters would be seamlessly filled by a pre-positioned spacecraft in the asteroid belt, whose data would then be relayed through a dedicated comms satellite at a Lagrange point to ensure a constant, high-fidelity stream to Earth. This would no longer be a hastily assembled coalition, but a single, distributed organism, a unified consciousness staring out into the void from a multitude of vantage points. It is a vision that borders on science fiction, yet it is the logical culmination of our desire to comprehend the cosmos in its fluid, uninterrupted entirety. The passage of 3I Atlas, therefore, is more than a scientific target. It is a dress rehearsal, a catalyst that could forge the protocols and ambitions for a new era of astronomy. Could this solitary traveler, in its silent passage, be the key that unlocks our potential to see the solar system not as a collection of points, but as a single, integrated field of view? As the object approaches its first major planetary encounter, the focus shifts from mere trajectory to tangible substance. The initial, distant observations can only tell us so much. The true character of a celestial body is often revealed not by its motion, but by its composition. The sophisticated laboratories orbiting Mars, NASA's MAVEN and ESA's Trace Gas Orbiter, are poised to perform a critical function. Their instruments, designed to sniff the tenuous Martian atmosphere for traces of methane and other gases, can be turned outward, their sensitive spectrometers aimed at the developing coma of 3I Atlas. They will conduct the first, crucial, sniff test, hunting for the spectral fingerprints of molecules like carbon dioxide, CO2, cyanogen, CN, and amidogen, NH2. These are the primordial building blocks, the volatile ices that sublimate as a comet approaches the Sun, creating the characteristic coma and tail. The specific ratios and abundances of these molecules are like a genetic code, allowing astronomers to classify the object, to place it within known families of comets or asteroids. A preponderance of certain compounds might suggest an origin in the Kuiper belt, while a different signature could hint at a birthplace in the far more distant Oort cloud. This chemical census is the foundational step in our understanding. But what if the chemical signature defies all known classification, presenting a mixture of isotopes or molecular ratios never before recorded in any catalogue of solar system objects? The mainstream scientific explanation would diligently work to fit any anomalous data into existing frameworks. Scientists would suggest that peculiar outgassing could be due to extreme thermal processing on a previous orbit, or perhaps the unique radiation environment of interstellar space has altered its surface chemistry in ways we are only beginning to model. The presence of unexpected molecules could be attributed to the breakdown of more complex organic compounds, a process known as photodissociation, driven by the Sun's intense ultraviolet light. According to current models of astrochemistry, the vastness of the galaxy allows for a wide variation in the initial conditions of planetary formation. An object from another star system could simply be a sample from a region with a slightly different abundance of elements, a testament to the diversity of cosmic creation. This line of reasoning is prudent, methodical, and grounded in the known laws of physics and chemistry. It seeks to normalize the anomaly, to bring the foreign into the fold of the comprehensible. Yet, that very act of normalization risks overlooking the most profound implication of the data. Does the desire to classify and categorize inherently blind us to the possibility of a truly radical departure from the known? This is where the speculative hypothesis emerges, not to contradict the scientific method, but to push its boundaries. The data from MAVEN and TGO will fuel a deeper, more contentious debate. Does 3I Atlas possess a natural composition that is merely uncommon, or does its chemical fingerprint suggest an origin that is, by our current definitions, abnormal? The term abnormal here transcends mere rarity. It implies a genesis or a history that lies outside our current paradigms of solar system formation. Could the ratios of hydrogen isotopes locked in its water ice, or the specific chirality of any complex organic molecules, point not just to another star, but to a fundamentally different process of formation? Perhaps it is not a pristine relic from a protoplanetary disk, but a fragment of a shattered planetesimal that formed in an environment rich in exotic materials, or even a manufactured object whose materials, while natural, have been processed, purified, or arranged in a way that leaves a subtle, artificial signature in its outgassing patterns. The instruments now training on it from Martian orbit were built to understand natural processes, and they will apply that rigorous, naturalistic framework. But what if the universe has crafted, or something within the universe has crafted, an object that deliberately blurs the line between the natural and the engineered? The sniff test, therefore, is more than a chemical assay. It is the first step in a much larger interrogation, one that will force us to re-examine our most basic assumptions about what is possible and what is waiting for us in the dark, silent spaces between the stars. As the spectral lines resolve on the monitors at mission control, will they reveal a familiar story written in a slightly different dialect, or will they spell out a vocabulary for which we have no translation? The cosmos, in its profound and silent choreography, occasionally sends messengers from the abyss. These icy nomads, the comets, are more than just celestial spectacles. They are cryptic archives, their very essence a chemical codex waiting to be deciphered. When the object known as 3I Atlas was identified not as a local denizen of our solar system, but as a true interstellar wanderer, the scientific imperative shifted from mere observation to a form of cosmic interrogation. We cannot capture it, we cannot land upon its enigmatic surface, but we can, from a distance, learn to smell its scent. The art of remote chemistry, the spectroscopic sniff test, thus becomes our primary tool, a way to inhale the faint exhalations of its coma, and, in doing so, to read the story of its origin written in the language of atoms and molecules. The Martian orbiters, MAVEN, and the Trace Gas Orbiter, TGO, now stand as our most sophisticated olfactory organs, their sensors tuned to the faintest chemical whispers on the solar wind, poised to classify the material composition of this visitor and to contribute a definitive chapter to the ongoing debate. Is 3I Atlas a product of a natural, albeit alien, process, or does it bear the unmistakable signature of an anomalous genesis? According to the established models of cometary science, the volatile heart of a comet, when warmed by the sun, sublimates, creating a glowing coma and often a tail. This outgassing is a predictable recipe of ices, primarily water, carbon dioxide, and carbon monoxide, inherited from the protoplanetary disk of its birth star. The initial spectroscopic data, captured in the ultraviolet and infrared bands by instruments like NOMAD aboard TGO, with its UVIS channel, spanning 200–650 nanometers, and its sophisticated infrared spectrometers, SO and LNO, would be expected to reveal this standard cometary cocktail. The presence of H2O, CO2, and CO in certain ratios would paint a picture of a familiar, if distant origin, a home-style comet born in a stellar nursery not unlike our own. The narrative would be one of natural universality, a testament to the common physical processes that govern star and planet formation across the galaxy. Yet, what if the very ratios of these common gases tell a different, more unsettling tale? What if the chemical fingerprint reveals not a nascent object, but one that has been profoundly aged and altered by an epic journey through the harsh, unforgiving environment of interstellar space? The first level of our analysis, therefore, is elemental, a simple detection. If the sniff test reveals only water and carbon dioxide in proportions consistent with comets from our own Oort cloud, the conclusion would lean towards 3I Atlas being a natural, if interstellar, analogue. It would be classified as a home-style comet, its composition a comforting, the mirror of what we know, its strangeness confined merely to its trajectory. But is the universe, in its infinite variety, so predisposed to creating carbon copies? The very fact of its interstellar origin suggests a history of ejection, a violent birth that could have imprinted upon its chemical soul. The second, more intriguing level of analysis begins with anomalies in these ratios. Should the data show a pronounced enrichment of carbon monoxide, a gas that is more volatile and susceptible to loss over time, or a curious depletion of certain other compounds, the interpretation becomes far more complex. A CO-rich, CN-poor, and NH, weak signature would not indicate youth, but rather extreme maturity. It would suggest a surface material that has been thoroughly baked, not by a single star, but by the cumulative exposure to cosmic rays and interstellar ultraviolet radiation over millions, perhaps billions of years. The weak bands of cyanogen, CN, and amidogen, NH, which are typically products of the photodissociation of more complex parent molecules in the inner coma, would imply that those parent molecules have long since been stripped away, leaving behind a scorched and primordial crust. This is not the fresh ice of a recently formed object, but the cosmic equivalent of a well-done relic, its original volatile budget spent on an unimaginable voyage. Could an object so thoroughly processed by the void still be considered a standard cometary body? Or does its chemically weathered state mark it as something entirely sui generis, a new class of interstellar fossil? The plot deepens further, with the potential detection of more exotic signatures. The precedent exists, etched into the recent history of Mars observation. When comet Siding Spring grazed the red planet in 2014, the MAVEN spacecraft, with its suite of instruments, including the Imaging Ultraviolet Spectrograph, IUVS, and the Neutral Gas and Ion Mass Spectrometer, NGIMS, performed a masterclass in remote chemical sensing. It did not just observe the comet. It sampled the Martian atmosphere after the comet's passage and detected a distinct, transient enrichment of metal ions, magnesium, Mg-Mi, and iron, Fe-Mi, deposited there by the comet's dusty coma. This was a definitive demonstration that one can, indeed, sniff the composition of a passing body by analyzing its impact on a planetary environment. Applying this proven technique to 3I Atlas, a heightened presence of such metal ions in its own coma or in the ambient solar wind it is ploughing through would be profoundly revealing. It would point towards a core of unusual solidity and mineralogical complexity, a nucleus far richer in refractory materials than the fragile, dirty snowball of conventional comets. This is not merely a clump of ice and dust, but perhaps a fragment of a shattered world, a piece of planetary crust blasted into the galactic dark. What strange geology could give rise to a wandering body so abundant in the fundamental building blocks of rock? And this leads us to the third, most speculative level of our chemical inquest, a hypothesis that stretches the boundaries of current astrobiology. What if, beyond the water and the metals, the sensitive spectrometers of TGO and MAVEN were to catch the faint, telltale spectral lines of complex, stable organic precursors? Not just simple hydrocarbons, but more resilient molecular structures, the kind that could serve as the raw materials for the chemistry of life. The detection of such compounds, having survived the object's long pilgrimage, would transform 3I Atlas from a mere celestial curiosity into a potential chemical courier. It would no longer be just a rock, but a container, a care package of prebiotic chemistry dispatched across the light years. The very stability of these molecules under such extreme conditions would suggest a robustness to the fundamental processes of organic chemistry that we are only beginning to comprehend. If the seeds of life's ingredients can not only form around other stars, but can also endure the unimaginable rigors of interstellar travel, then the game of hunting for the source materials of life has indeed entered a new, and vastly more promising, chapter. Does this interstellar visitor carry within its chemical code not just the history of its birth, but also a promise, a demonstration that the universe is not only capable of, but perhaps teeming with, the very compounds that led to us? Yet, as we extend our senses to smell this visitor, we must also consider the environment through which we are perceiving it. The act of observation itself is not without its context, nor its potential perils. The precedent of Siding Spring serves as a stark reminder that a comet's influence extends far beyond its visible form. In 2014, the dust and ions from its coma, though tenuous, created significant disruption in Mars's magnetosphere and ionosphere for several hours, a temporary but measurable rewiring of the planet's immediate space environment. This historical data point forces a crucial, contemporary question. If a comet from our own solar system could cause such a stir, what might the passage of a true interstellar object, with its potentially unique composition and dust properties, entail? While 3I Atlas is predicted to pass at a farther distance, its unknown nature leaves room for uncertainty. the very instruments we rely upon for communication with our orbital sentinels, the delicate network of telecommunications that links TGO, MAVEN, and their robotic companions back to Earth, operate within this vulnerable envelope of space. Could the subtle interactions of 3I Atlas's coma with the solar wind generate a shower of charged particles or a cloud of fine, abrasive dust that introduces noise, interference, or even temporary blackouts in our vital data streams? The scientific pursuit of knowledge is often a dance with the unknown, and in reaching out to understand this stranger, we must acknowledge that its mere presence could, in ways we have yet to model, alter the very medium through which we seek to understand it. After all, what are the true risks of inviting an unknown guest into our celestial neighborhood, even for a brief, passing moment? A comet once bathed the red planet in a sea of alien plasma, an event both transient and profound, witnessed by our silent sentinels in orbit, and now preserved in the digital annals of our species' quest for knowledge. That celestial visitor, known as Siding Spring, did not strike the Martian soil, yet its passage was far from inconsequential. Its immense coma, a shroud of gas and dust, stretching over 1 million kilometers, swept across the Martian system, and for a few fleeting hours, the very space around Mars was no longer its own. The planet's delicate magnetosphere was stirred, its ionosphere was scrambled, and a meteor shower of cometary dust painted the thin, cold atmosphere with ephemeral, metallic streaks. This event, a precedent etched in the data streams of the MAVEN orbiter, stands as a stark reminder that the vacuum of space is not empty, but is a dynamic medium, susceptible to the influences of passing ghosts from the outer dark. And so, as another visitor, the interstellar comet 3I Atlas continues its own solitary journey through our cosmic neighborhood. A question of profound operational and philosophical significance arises. Could this distant wanderer, passing at a far greater remove, still impart a whisper of disturbance, a subtle static upon the lines of communication that bind our robotic explorers to their creators on the pale blue dot? The question is not one of cataclysm, but of nuance, not of impact, but of interference. Could the faintest breath of its coma, a wisp of ionized gas and microscopic dust, introduce a ripple into the carefully managed radio silence between Earth and Mars, forcing our machines to listen a little harder through a newfound cosmic noise? According to current models of cometary physics and planetary interaction, the primary risk factor is one of sheer proximity and density. The cometary coma is a tenuous structure, its particle and ion density decreasing with the square of the distance from the nucleus. A small change in distance precipitates a precipitous drop in potential effect. In October of 2014, comet Siding Spring performed an exceptionally close flyby of Mars, its nucleus passing within a mere 136,000 kilometers, a hair's breadth in celestial terms. This allowed the densest regions of its coma to directly engulf the planet, resulting in the significant, albeit temporary, magnetospheric and ionospheric disturbances so meticulously documented by our instruments. In stark contrast, the trajectory of 3I Atlas places it at a vastly more remote distance of approximately 30 million kilometers during its closest approach to Mars. At such a remove, the density of particulate and ionized material reaching the Martian system is calculated to be reduced by several orders of magnitude, rendering the probability of any measurable, macroscopic environmental effect virtually negligible. The mainstream scientific explanation, therefore, leans heavily towards a conclusion of minimal risk, suggesting that the cometary influence will be lost within the constant background chatter of the solar wind and the inherent thermal noise of the cosmos itself. The spacecraft in orbit and on the surface would, in all likelihood, register nothing more remarkable than the passage of another distant, icy body, its presence noted by telescopes but unfelt by the sensitive apparatus of telecommunications. But what if our models, for all their mathematical elegance, fail to capture the full, subtle texture of reality? The precedent of Siding Spring demonstrated that a comet's influence is not a simple, monolithic event, but a cascade of interconnected phenomena. While the direct blast of plasma has subsided by the time it travels 30 million kilometers, could there not be more ethereal, more persistent structures propagating through the interplanetary medium? The solar wind itself is not a uniform stream, but is riven with discontinuities, magnetic filaments, and pressure waves. The introduction of a significant source of foreign ions and dust, even from a great distance, could potentially seed a large-scale, albeit weak, disturbance in this flow. One might hypothesize the formation of a vast, invisible, plasma shadow, a subtle gradient in charged particle density that slowly drifts across the path of Mars. This would not be a storm, but a gentle tide, a region of space ever so slightly more electrically conductive or more turbid with microscopic particulates. As a radio signal traverses this region, could it not experience a slight, almost imperceptible phase shift, a faint scintillation, a minute increase in signal-to-noise ratio that would require the communication systems to momentarily boost their power or recalibrate their error correction algorithms? The effect would be minor, a ghost in the machine, easily compensated for by modern engineering protocols, yet its very existence would speak to the interconnectedness of all things in the heliosphere. Could the faintest echo of a comet's breath, stretched across millions of kilometers, still be enough to leave a fingerprint on our attempts to converse across the void? This leads us to the first, and most probable, tier of our escalating hypothesis, the scenario of a minor background enhancement. Here, the passage of 3I Atlas would result in no operational disruption whatsoever. The deep space networks on Earth and the transceivers on the orbiters would continue their dialogues uninterrupted. However, in the raw data streams, buried beneath layers of processing and filtering, a post-analysis conducted by meticulous scientists might later identify a statistically significant, yet operationally irrelevant, uptick in background electromagnetic noise across certain frequency bands, particularly those sensitive to plasma oscillations. This would be the cometary equivalent of a distant, gentle sigh, heard only by the most sensitive of microphones in an otherwise silent room. It would confirm a physical interaction, a tangible, if minuscule, link between the interstellar object and our planetary outpost, but it would not necessitate a single change to any mission timeline or communication schedule. The event would pass from an operational non-event into a scientific curiosity, a data point affirming our understanding of the diffusion of cometary material through the solar wind. But is the transition from undetectable whisper to measurable signal truly a binary one? Or does there exist a grey area where the whispers of the cosmos begin to form coherent words? We must then consider the second, more speculative tier, the possibility of a localized plasma ripple. This hypothesis ventures beyond a uniform background increase and posits the existence of transient, denser structures within the broadly dispersed cometary material. Cometary comae are known to be heterogeneous, with jets and outbursts creating clumps and filaments of higher density that can be carried outward by the solar wind. While these structures would be dramatically diluted over 30 million kilometers, it is not entirely beyond the realm of possibility that a particularly robust filament, a coherent strand of ionized gas, could survive the journey and intersect with the Martian system. The effect would be highly localized in time, lasting perhaps only a few hours. For a brief period, the plasma density in the immediate space around the Martian orbiters could rise above a critical threshold, causing increased scintillation for radio signals passing through it. This could manifest as a temporary degradation of signal quality, a fuzziness in the high-rate data streams carrying images or scientific data. In such a scenario, mission controllers, forewarned by the comet's well-tracked trajectory, might elect to implement a minor duck and cover protocol, not for physical protection, as was considered in 2014, but for communications integrity. They might reschedule a non-critical data transmission for a later time or switch to a more robust, lower bandwidth encoding for the duration of the event. It would be a testament to our learned prudence, a carefully choreographed dance to avoid a potential, minor inconvenience. Yet, this very act of avoidance raises a deeper question. In our efforts to shield our machines from every conceivable cosmic variable, do we risk insulating them from the very phenomena they were sent to observe, thus filtering out the faint, unexpected signals that often herald the greatest discoveries? And from here, the path of speculation leads us to its third and most fantastical tier, a narrative woven from the threads of known physics, but stretched to its imaginative limits. Let us envision a perfect, and perfectly unlikely, storm. Imagine that 3I Atlas, in the final stages of its approach, experiences a significant, unanticipated outburst, releasing a dense cloud of fine, micron-sized dust grains. Simultaneously, a coronal mass ejection from the Sun, a parcel of intensified solar wind and magnetic field, is launched on a trajectory that places Mars directly in its path. The timing is exquisitely precise. The wave of solar energy overtakes and compresses the cloud of cometary dust, accelerating the particles and charging them triboelectrically. As this combined front reaches Mars, it does not deliver a gentle ripple, but a miniature, hybrid storm. The infall of these hypervelocity dust particles into the upper atmosphere, now supercharged by the solar event, could theoretically induce a novel atmospheric phenomenon, a proton aurora. Not the familiar, shimmering curtains driven by solar electrons, but a more diffuse, global, luminescence generated by the bombardment of energetic protons liberated from the atmospheric molecules by the impacting dust. This sudden, planet-wide ionization event would act as a variable shield, absorbing and scattering specific radio frequencies. For a few critical minutes, long-range communications between the orbiters and Earth could be severely attenuated or even completely severed, triggering automated safety protocols. The network, designed for resilience, would seamlessly switch to backup channels, perhaps utilizing the European Space Agency's relay infrastructure as a temporary measure until the ionospheric disturbance subsided. This would be a moment of high drama entirely confined to server logs and contingency reports, a silent, invisible storm that briefly isolated a world of machines. But if such a chain of events, however improbable, were to occur, would it not fundamentally alter our perception of risk, forcing us to consider not just the primary actors on the cosmic stage, but the potential for their chaotic, impromptu collaborations? The legacy of Siding Spring, therefore, is not one of fear, but of foresight. It provided a crucial data point, a real-world stress test that has been meticulously integrated into the risk management paradigms of all spacefaring agencies. The experience of 2014, combined with the vast distance of the 2025 encounter, has led to a posture of vigilant calm. The procedures for spacecraft protection and communication scheduling have become increasingly standardized and robust, capable of handling a spectrum of disturbances from the solar wind's constant variability to the hypothetical whispers of a distant comet. The orbits of our assets are known, the trajectory of the comet is tracked with exquisite precision, and the models of interaction are continuously refined. The response is not one of alarm, but of informed readiness, a demonstration of how humanity learns to operate within a complex and dynamic cosmic environment. We have moved from reactive surprise to proactive preparation. Yet, does this very mastery over the predictable variables blind us to the potential for the truly anomalous, the single, unanticipated data point that could unravel our most carefully constructed models of the cosmos? This meticulous process of observation and analysis, of course, stands in stark contrast to the chaotic noise of misinformation that so often accompanies celestial events. As the science teams calmly assess the negligible risk posed by 3I Atlas to the Martian outpost, a separate, parallel narrative has begun to ferment in the darker corners of the global conversation, one that ignores the red planet and sets its sights on a far more familiar target.